So thanks for the invitation to be here. It's very nice to be in Santa Barbara. I want to thank Victor for the very nice overview of quantum error correction. And I gotta say, as I was listening to Victor talk about the 4-qubit code continuously throughout his talk, I got more and more nervous for my own talk, because in some sense he was spending all his time talking about the simplest possible codes. And I'm going to tell you about some of the more complicated codes that were developed just within the past year. So difficulty spike felt more like a step function the more he spent time talking about these codes. But the topic of my talk is going to be some recent developments in what are so-called asymptotically good quantum Ldpc codes. And Victor already defined some of these notions already, but I will do so in more detail. So the first thing we have to talk about is what exactly are Ldpc codes and why exactly should we care about them. So Ldpc stands for low density parity check. And effectively, these are codes that have extremely succinct descriptions. It only needs a constant number of checks to define every logical qubit in essence. And so you can very efficiently write down descriptions of these codes. And these codes end up being extremely efficient codes. And I mean efficient in many senses of the word. They're efficient in the sense that they have very good descriptions. They're efficient in the sense that they are sort of physically motivated. Every qubit only has a constant number of interactions acting on it. So that makes them very amenable to theoretical study. And they are sort of also the only real possibilities you have at getting experimental handles on these things, because the amount of interactions you can really physically control are very much limited in a physical sense. And they're also efficient in the traditional sense of the word, as we'll see, in the sense that they are some of the best codes that we have access to in a very mathematical way. So there are two types of Ldpc codes. So there are classical ones and there are quantum ones. And classical Ldpc codes have a very long history. And they are sort of the gold standard in classical error correction. Most of the technology that we have today uses Ldpc codes in some way. For example, Wi-Fi, 5G networks, your solid-state drives, they all employ error-correcting codes, which are Ldpc. And so one of the questions is, how can we, as quantum information theorists, try to approach this classical gold standard? Why would we care about this as quantum theorists? Well, quantum Ldpc codes are expected to have extremely good fault tolerance properties. And one example of this is sort of a breakthrough result by Gottesman in 2013 that tells you that if you have a sufficiently good quantum Ldpc code, you can achieve fault-tolerant quantum computation using a constant number of qubit overhead. And so if we really want to push through, this is sort of beyond near-term quantum computing, but if you really want to look towards into the far future and sort of have the best possible chance and most efficient possible architectures for quantum computation, then perhaps good Ldpc codes and efficient Ldpc codes are where we should be looking at next. Beyond applications, physical applications, there are also very deep connections to mathematics and many-body physics and complexity theory. So, for example, the development of these good Ldpc codes in recent years have led to advances in producing so-called classical locally testable codes, which are very prominent in computer science. They've led through complexity theory results in something called the sum of squares hierarchy in direct refutations of constraint satisfaction problems. And more recently, as Chinmay will tell us next, there's this breakthrough result in the proof of the NLTS theorem that directly uses some of these developments. So it's really a topic which is at the heart of a lot of recent developments, both in terms of theory and in terms of application. And finally, I'll just mention that most of the codes, perhaps all of the codes that we really truly care about are Ldpc to begin with. It's kind of easy to forget because it's not really emphasized, but toric code has wait for checks, and so they are by definition also Ldpc codes. But the type of Ldpc codes I'm going to talk about are so-called good codes. Not that the Tora code is not a good code. Good here has a very technical meaning in the sense that they can encode effectively as many qubits as possible within each block and correct as many errors as possible within each block. And all of this really gets down to a very fundamental question, I think, a question of independent interest, which is what exactly is the fundamental limitation to efficient quantum information storage? So there has been a explosive development in quantum LDPC codes in the recent years. You can kind of see this timeline here. So on the very left, this is Kitaev's Tora code in 1996, 1997. And then for about 25 years, we've been stuck at a distance barrier for LDPC codes of around square root n. So this Friedman-Meyer low code was sort of the record holder for how much distance you can get in an LDPC code. This was, I believe, around 2002, 2003, 2002 by the timeline here. And this record stood all the way until this blue line right here by Evra, Kaufman, and Zimmer, which finally broke this distance barrier, but still not really the square root barrier. They achieved kind of logarithmic advances on the square root barrier. And it wasn't really until Hastings and O'Donnell with their fiber bundle codes that the square root distance barrier was really broken. And one thing that you'll notice is that from the development of the Tora code all the way here, there really hasn't been much going on in terms of distances. And then all of a sudden, around 2020, a very large number of sequences of work have made increasing number of progress. And all of these works kind of squished together here are within months of each other. And finally, this culminated in just last year, 2021, with the actual proof by Panteleev and Kalichev of the very first asymptotically good, so in essence, the best mathematically possible quantum error correcting code. What we're going to talk about is a specific variation here by the very last two authors here, Levy and Zemmour, that kind of simplify Panteleev and Kalichev's construction, but still very much uses a lot of the same mathematical ingredients. And that's what we're going to spend most of our time talking about today, how to construct and understand these quantum LDPC codes. And one thing you can kind of ask, one thing that's kind of curious is what exactly led to this flurry of activity around 2020? And at a surface level, it's sort of the development of better products, better ways of taking products using symmetry and combining different codes into better codes. But at a more fundamental level, I don't think we truly understand what exactly the magic behind good quantum LDPC codes are. And one of the reasons I say that is we now have several kind of different constructions of good LDPC codes, but they all involve the same fundamental ingredients. They're all kind of variations of the very same construction at the fundamental level. And so we sort of know sufficient ingredients for LDPC codes, but we don't know what truly is necessary for them. And it'd be kind of nice to abstract away from the very concrete constructions we have and to have a general framework for understanding what exactly is needed to construct a good quantum LDPC code. And so that's sort of kind of an open-ended, open problem, if you will. So to begin talking about quantum LDPC codes, I'll very quickly talk about classical LDPC codes. And this will just be like a lightning review, mostly to set notation. So a classical error correcting code is just going to be a subset, a subspace of f2 to the n, so just a subspace of bit strings, if you will. It'll be very convenient for us that this classical error correcting code is specified by something called the parity check matrix H. And what the parity check matrix is they define the checks. So in the quantum case, these would be the stabilizers effectively. And the error correcting code is just defined as the kernel of this matrix. If the matrix has rank n minus k, then we say that this subspace, this code, encodes k logical qubits into n physical bits here. And the distance of the code is effectively the smallest distance between distinct code words inside the code, or since this is a linear code, the weight of the smallest non-zero element. We're going to talk about code families, and this is where the adjective good comes from. We say that a code family is asymptotically good if the number of qubits it encodes and the amount of error it can correct are all scaling linearly with the number of physical bits it encodes. And this is the same definition for quantum error correcting codes as well. And this is sort of effectively the best possible rate and distance you can really hope to achieve with any sort of error correcting code. And finally, we say that the code family is Ldpc if the row weights and the column weights of this parity check matrix H in the code family is bounded above by some constants. The construction I'm going to talk about is called the quantum Tanner code construction. And before I tell you about the quantum Tanner code construction, I first have to tell you a bit about what are called classical Tanner codes. And classical Tanner codes are families of classical error correcting codes which form good Ldpc codes. And they're sort of one of the more prominent constructions of good classical Ldpc codes. And these are graphical based codes. So what you first do is you take a delta regular expander graph. And if you don't know what an expander graph is, I'll tell you in a bit. But for now, you can just think of it as a very highly connected graph. So we take this graph gamma, and we are also going to fix what is called a local code or a base code C. And we're going to require that the length, the block length of this code matches the degree of the graph. And if we fix our attention onto the edge neighborhood of a single vertex, what's called a local view, how we specify the Tanner code is we're going to require bits be placed on the edges of this graph. And we're going to say that a bit string defined on this graph belongs to the Tanner code if and only if the restriction onto each local view belongs to our choice of base code. And so this is a two-piece construction. It consists of a global expanding geometric scaffold in the graph gamma. And it also consists of a local error correcting piece in the base code C. And together, this construction of placing local checks at vertices and bits on the edges is called the Tanner code construction. And this was first sort of developed, this was kind of rediscovered many times, but it was really popularized in the work of Sipser and Spielman in '96 in a famous paper called expander codes. These are also called expander codes because they're based on expanding graphs. Although sort of confusingly in the quantum case, quantum expander codes and quantum Tanner codes are different objects. So these are words that kind of have the same technical meaning in the classical sense, but have diverged a little bit in the quantum case. So let's talk a bit about expansion. And the moral definition of what an expander graph is it's a graph that allows you to amplify local properties into global properties. And I won't even really tell you, so my talk is really meant to be a high-level overview without much technical detail. And so I won't really tell you what the proper definition of an expander is. Rather, we're going to take an operational definition just in terms of the properties of the graph that we need. And the only real property we need is something called the expander mixing lemma. And this is how I'm going to define expanders in my talk. So we're going to say that a graph is called a lambda expander for some parameter little lambda here if it satisfies the expander mixing lemma. And you can't actually leverage this into a full proof because the expander mixing lemma is if and only if. But what the expander mixing lemma roughly says is that if you have a graph which is a delta regular expander, you can take any two subsets of vertices, and you can look at the number of edges between these two sets counted with multiplicity. And on the right-hand side is sort of the edge density. This delta over V is the kind of the edge density inside the graph, multiplied by the cardinalities of the two sets. And this is sort of the amount of edges you expect between S and T if you pick the graph to be completely random amongst delta regular graphs. And so what the expander mixing lemma tells you is that expander graphs are graphs which look roughly random as you examine edge sets between different vertices. And the amount of closeness you get to randomness is controlled by this parameter lambda here. And so the smaller the lambda, the more expanding the graph is. And the optimal lambda you can kind of hope to achieve for a family of graphs is a lambda that scales roughly as the square root of delta. And it's going to be important for us that we can find very good expander graphs, graphs that essentially achieve this parameter scaling of square root delta for a lambda. And it turns out that's quite easy because Friedman showed that if you pick a random delta regular graph, with high probability, it's going to be essentially the best possible expander. And there are explicit constructions of so-called Ramanujan expander graphs by taking certain groups and constructing their Kavli graphs. And that's the type of graph that we're going to use. So I'm going to give you a flavor of what I mean by expander graphs amplifying local properties to global properties. And this is not really something that's technically relevant for proving distance in the quantum case. I just wanted to give you a flavor of how these types of proofs go, because I can't actually sketch any of the technical details in the more involved quantum distance case. So take a Tanner graph with some expanding graph, say a Tanner code with some expanding graph gamma. And we're going to take a local code that has distance, some little delta multiplied by the block length. So this little delta is called the relative distance. And we want to prove a distance bound for the overall Tanner code from the distance of the local code C. And so what you can do is you can take a non-trivial code word X inside the Tanner code, and you can take all the positions where X is 1, and this will pick out a set of edges for you, and it's going to induce for you a subgraph gamma prime here. And because of the fact that at every vertex, it needs to be a code word of little c, by definition, this induced subgraph must have a rather large local degree. I'm not going to do the algebra, but using the expander mixing lemma in this and a bit of algebra, you can show a degree bound. You can show that the number of vertices inside your induced graph gamma prime is bounded below linearly by the total number of vertices present in the overall expanding graph. And this immediately tells you that as long as this quantity here is non-negative, as long as you can choose delta sufficiently small, smaller than this parameter, lambda sufficiently small, smaller than this parameter delta over 2 here, which is always possible for a sufficiently good expanding graph, this will imply that any non-zero code word you have is bounded linearly below by the overall, by some constant times the overall block length of your code. And so this is an example of lifting kind of a local distance into a global distance. And it turns out that there are other things that can be lifted locally to globally as well. And the thing that's relevant for quantum codes is how well the local codes fit together. More technically, it's a property called testability that we're going to talk about. So I'm not going to talk too much about this because Victor has already kindly talked about this, but all of the codes we're going to talk about are CSS codes, and CSS codes are just stabilizer codes where all the stabilizers can either be put into X, purely X or purely Z type. And so you can write the parity checks of a stabilizer CSS code in terms of sort of a block diagonal decomposition. You can define classical codes as the kernels of these two block matrices. These will define codes for you CX and CZ, called the constituent codes of the CSS code. These two codes are required to satisfy the CSS condition so that the actual checks still commute with each other and they define a proper stabilizer group. And the distance of the CSS code can be kind of talked about in terms of the distances of the classical codes. They are the smallest code words within the classical codes, which are not within the duals of the code of the other type. So these are sort of the smallest logical operators you can have. We say that a quantum CSS code family is Ldpc if the constituent codes, the classical constituent codes themselves are Ldpc. And this immediately actually gives us some tension and illustrates why constructing very good quantum Ldpc codes becomes a little problematic. Because what happens is that the CSS condition requires that the dual of one of the codes lie within the other code. So if you want CZ to be a very high distance code, as you would intuitively expect if you want a good Ldpc code, then anything inside it must be high weight. But these are precisely the stabilizer generators. So this tells you that if CZ really were a good code, all the code words inside it must have large weight, and that sort of is in tension with wanting low weight stabilizers. And finding a way to both preserve quantum distance and also have low weight checks becomes the defining problem of finding a good quantum Ldpc code.
I had a question related to this. So are all the known constructions of quantum Ldpc codes of the CSS type, or are there other?
Most of them are of the CSS type, but I don't think all of them. All of the good Ldpc codes that we have right now are of the CSS type.
Okay, thanks.
So roughly the ingredient for a good quantum Ldpc code comes in two types, just like in the classical Tanner code case. We must have a way of stitching together these two classical codes to form a well-defined and good quantum Ldpc code. And this involves both a local component and a global component that we're going to talk about. So globally, what happens is the stitching is accomplished, roughly speaking, using something called a balanced product. And what a balanced product does is it takes two G-symmetric graphs, so graphs that have some free group action acting on it, and it effectively quotients out this symmetry to produce a smaller graph that contains each of the two graphs within it as a constituent. More formally, as Victor kind of hinted towards, it's more proper to look at this as a product on the underlying chain complexes defining these graphs. But for our purposes, we're going to give a completely explicit description of what this complex is going to be. So we're going to take two symmetric graphs, and we're going to actually get a higher dimensional object that not just has vertices and edges, but also faces. At a local level, we also have to make appropriate choices of the local codes to ensure that the two CSS codes are compatible with each other and that the resulting code has good distance. And what we're going to see is that the local compatibility of the codes is going to be amplified by the expansion of the first piece here into a more global compatibility. And this is what makes the magic of this construction work. And so now we get into sort of the more technical pieces of the construction. So the geometric expanding object we have is now called in the literature something called the left-right Kavli complex. And this was sort of first outlined in a classical coding theory paper, also implicitly inside the original construction of quantum Tanner codes. And this is, as I said before, really an instance of the balanced product introduced by Nico Bruckmann and Jens Eberhardt. And the construction is as follows. We're going to take a group G, What this group is not really important. It's some kind of projective special linear group. But what's important is that we're going to take this group G. It's really a family of groups, actually. Groups that grow with size, so we can have a family of graphs. And what you can show is that for this family of groups, we can always find two sets of generating sets of constant size, of the same constant size delta. And this will be the regularity of the underlying graph. And we're going to define the left Kavli graph. So the A is on the left, reminding you that group multiplication acts on the left in the first graph. We're going to take a left Kavli graph defined by the generating set A. And we're going to take a right Kavli graph defined by the generating set B. And we're going to define two bipartite lambda expanders using these Kavli graphs. So the fact that these can be expanders just comes from a long line of work back in the traditional literature of Ramanujan graphs. And the fact that these can be taken bipartite is sort of without loss of generality. If they're not already bipartite, just take the bipartite cover, which is an operation that preserves expansion. So we're going to take these to be bipartite delta regular lambda expanders, just like in the traditional classical Tanner code case. And so from these two pieces, we're effectively going to construct a product. And instead of telling you how to do the product, I'm just going to talk to you about what the geometric components really are. So these two graphs define what is called a left-right Kavli complex. And this is a two-dimensional complex that consists of faces Q, vertices V, and edges E. So for the vertices, it's just going to be the underlying vertex set of these two graphs. So it's the double cover of the group. The edges are going to be partitioned into two disjoint sets, the ones belonging to the generator A and the ones belonging to the generator B. So for every vertex, so G is some group element and I is just some index modulo 2, we're going to have an A-type edge for some choice of A in the generating set A, where G goes to AG on the left, because this is the left Kavli graph. And then we also preserve bipartiteness by taking the index to be I plus 1 modulo 2. And same thing for the B-type edges, except we use the other generating set and we multiply on the right. And finally, we're going to have a set of faces, which are really squares. And a square is just a set of 4 vertices of the form. You start at some anchoring vertex Gi, you take some A-type edge, you take some B-type edge, and then you walk and complete this square along the sequence. And you can always choose, it's shown that you can always choose a technical restriction, something called total non-conjugacy, that ensures that you can choose the generating sets A and B in such a way that the squares actually are squares, that they have 4 non-coincident vertices so that they're non-degenerate. So this is, roughly speaking, a very bad illustration of what this complex would look like. It really is a much more high-dimensional object and not really a proper lattice like this. But you have sort of a bipartition of vertices in black and white. So you can imagine that the white vertices are of one type, say 0, and then the black vertices are of a second type. You have edges of A type, and you have edges of B type. And at a vertex, any choice of a edge and a B edge will define for you a square face. And so how we define the code is that classically, a Tanner code places bits on the edges of some kind of graphical object. In the quantum Tanner code case, we're going to go one dimension up. Instead of placing bits on the edges, we're going to place qubits on the faces and still require that the stabilizers are supported on the vertices themselves. So we're going to choose 2 local codes, CX and CZ. This is not the constituent code of the Tanner code of the CSS code itself. This is just one of the pieces defining these codes. But what we're going to do is we're going to choose stabilizers at every vertex. So for example, all the white vertices are going to be X-type stabilizers, and all the black vertices here are going to be Z-type stabilizers. And we're going to require that the stabilizers be indexed by code words of these two codes that we're going to choose. And there are specific conditions that have to be met to ensure that this actually defines a proper quantum code. So this two choices here would not work, for example, because it does not satisfy the CSS condition. And it turns out that there's a natural way of imposing this condition. So because every check type is of either X type if it belongs to a white vertex or Z type if it belongs to a black vertex, this automatically defines for you a CSS type code. And to visualize what the underlying constituent codes of the CSS code actually is, it becomes convenient to introduce two auxiliary objects called the face graphs. And because of the non-conjugacy condition, what you can guarantee is that every face contains 4 vertices, 2 of which are white and 2 of which are black. And so what we're going to do is we're going to define 2 graphs. We're going to connect the diagonals of the faces along the black vertices so that every edge uniquely identifies a face in this graph. And so this will be called one of the face graphs gamma square X, for example, or maybe this is Z, I forget which type of checks I place on which. And then also the same thing on the white diagonals. And so now we have 2 auxiliary graphs where every edge corresponds to a face. And what we can do now is we can mimic the original construction of the Tanner codes. So now the qubits are on the edges of these face graphs now, and it turns out that the classical codes that define the CSS code are now the Tanner codes defined by these 2 face graphs, which will inherit expansion because the underlying geometric complex is expanding, together with local codes, which are the duals of the stabilizers, right? The stabilizers are the checks, and so if you want a code word of these codes to define your quantum correcting code, these belong to the duals of these codes. And the overall quantum Tanner code is now the CSS code defined by these 2 classical Tanner codes. The very last piece I need to tell you about is what exactly the local codes must be. So this is what the actual local view around every vertex looks like. It's sort of a collection of pages, if you will. And for every choice of an A edge and a B edge, so for example, B1 here and A2 here, you will always have a square defined by these 2 edges. And so what you can do is that you have delta A edges at every vertex and delta B edges at every vertex. And so this defines for you a bijection to a delta by delta matrix. So local code words are matrices supported at the vertices of this complex. And it turns out that in classical coding theory, there's a very natural way of representing code words as matrices using something called the tensor product code. And so what we're going to do is we're going to introduce an additional layer of structure. We're going to pick 2 more codes, C1 and C2, in such a way that CX and CZ are what is called the tensor product of these 2 codes. And what a tensor product code is it's a code word which is a matrix in such a way that every column is required to be a code word of C1, and every row is required to be a code word of C2. So suppose we pick some CA and CB, and we defined our CZ to be one of these tensor product codes. Well, 2 stabilizers can overlap if and only if they share some edge within the complex. So if we already picked all of our Z stabilizers, this corresponds to a matrix here and a matrix here on a shared column or row. And so these things are indexed by a code word of CZ. And what we're going to require is that the checks of the other type belong to the dual code. And so what this tells you that if we've already picked CZ to be some code, what we need to do is we need to pick the stabilizers of the other type to consist of the tensor product of the duals. And this will automatically satisfy the CSS condition for you. I'm running a bit out of time, but I will tell you the very last ingredient, which is something called local testability. To ensure that you actually get a good quantum Tanner code, there has to be an additional ingredient for you. What this ingredient is the dual codes of these things are called dual tensor codes. And what they are is that they consist of sums of matrices whose columns belong to one type of code and whose rows belong to the other type of code. And you need these codes to satisfy something which is called a robust testability condition. And what this condition is basically you cannot allow miraculous cancellations in these codes. So imagine you have a code of this dual tensor code that you know is low weight. Now, one way that can happen is if the constituent column and row parts are themselves low weight, which means that this thing has a large zero block inside it. Another possible way is that maybe the constituents are both of high rank, and there is somehow miraculous cancellation between the code words of the first type and code words of the second type that somehow allow you to get low weight sums, even though the constituents are high weight. And roughly speaking, robust testability tells you that this cannot possibly happen. And consequences of this are that these two are really the same property, kind of defined in different ways. They're equivalent to each other. It tells you that if a pair of codes is robustly testable so that these cancellations can't happen, well, one of the things it implies is that all of the rows and columns inside the code words of this dual tensor code are actually close to code words of either CA or CB. And moreover, you're guaranteed in the tensor case that if you have a code word where every column is close to the code words of CA and every row is close to the code words of CB, that you can stitch them together and form a valid code word of the tensor product code. Technically, for the purposes of a quantum Ldpc code, we really need a stronger condition where both the duals of these codes and the primary codes themselves satisfy this condition, but it's been shown that randomly chosen codes satisfy this property. So now we are finally ready kind of for our very last piece, which is a sketch of how the distance of these codes behave. So one thing you can do is you can kind of consider a code word X that has sufficiently low weight. And by the discussion above, because there are no miraculous cancellations, you're guaranteed very large zero blocks within a lot of the local code words. And this guarantees for you that the local code words have lots of rows and columns which either belong to CA or CB. These we'll call good local views. So for example, here all the green ones are the good local views, and these have rows and columns that actually belong to CA or CB. And what you're guaranteed is that you're always going to be able to find a vertex of the opposite type such that all of its rows and columns are now code words of CA and CB. And by robust testability, this kind of guarantees you that the thing supported on this vertex is going to be close to a stabilizer. And what you can do now is that for a sufficiently low weight code word, you're guaranteed to always be able to reduce its weight continuously by adding stabilizers to it. So it must have belonged to the stabilizer in the first place, so it cannot affect your quantum distance. And that, in a nutshell, is sort of how quantum Tanner codes work. I'm quite a bit over time. I apologize. I did have a few more slides, but I think I'll just end here and take any questions that you have.
Thank you very much, Eugene, for this very nice talk. And yeah, we are a bit over time, but we still have time for a few questions.
Yeah, I guess maybe we're going to talk about it in the next part, but the decoding problem, I think you.
Yeah, so I do have a few more slides on decoding problem. So what you can show, I'll skip over the details and just tell you the punchline. So there's a decoding problem for these quantum Tanner codes, which is how to effectively correct codes on them. And what you can show is that by very much the same type of proof, you can always find a flip set supported on the local view of a single vertex, such that you can flip that thing and reduce the syndrome weight effectively. And so this is very close to what is called the small set flip decoder of hypergraph product codes, if you're familiar with what that is. And so what we showed, along with several other groups in tandem, is that these quantum Tanner codes, and effectively all the known constructions of quantum Ldpc codes now, the good ones, support linear time decoders that iteratively allow you to decrease syndrome weights until you can get a good correction. Maybe I'll just, let's see. So this is effectively the decoding procedure. You define something which is effectively a syndrome weight, and you have to show that you can always find a flip set locally that can decrease the syndrome weight step by step. But once you've shown that, it becomes very straightforward to actually define the decoder.
So in your construction, you sort of built out this Kavli complex. You started with a group and you built out your complex out of it.
Yeah.
But it seemed like you said that you could also just take two graphs, provided that they have some shared symmetry. You could just, there's a notion of a product between them. Yeah.
So there's two ways of looking at it, and they're useful for different things, I guess. So in the very first construction of good Ldpc codes by Panteleev and Kalichev, they took this product approach. So what they did was they took two actual Tanner codes, classical Tanner codes, each of which consisted of one of these G-symmetric Ramanujan graphs, and they took their product. And they showed that the resulting complex, when interpreted as a code, a quantum code, is a good code. The difficulty with this procedure is that when you take the product, it's sort of inhomogeneous in the sense that qubits are no longer supported just on the faces, but on faces and vertices. So you kind of have to deal with two different types of qubits. And moreover, the local code is no longer as clean as the construction, which was later kind of cleaned up a bit and simplified by Levy and Zemmour in this quantum Tanner code construction. And so mathematically, it seems actually more elegant to take the product approach, but constructively separating out the global piece and the local piece allows a much easier time actually analyzing these things, which is why a lot of the work has been done on the quantum Tanner code construction.
But the Tanner codes you can still think of as a version of some sort of product?
The Tanner code, so this left-right Kavli complex itself can just be seen as a balanced product of graphs, not codes of graphs. Yeah.
Thank you.
So I've vaguely heard that to prove these results, you need graphs with kind of degree 1,000 or 10,000 or things like that. Could you comment on what types of models we're talking about, in case, just for more to ground it in more concrete?
The main difficulty, and this is sort of also another open problem, again comes with the desire of this, well, the necessity of the local codes. So because we don't really have explicit examples of codes that satisfy this robust testability, what we do is we show probabilistic existence. So this is what kind of computer scientists call a constant amount of non-constructivism. And you don't really know how large the block length has to be until you have high probability enough that one of these codes actually exists. So the best you can do is kind of give an estimate of when codes actually become, with high probability, robustly testable. And this kind of sets a lower bound on the degree of your graph. So it's not really the degree of the graph itself, which is problematic. It's the lack of control over the local error correcting piece that is kind of problematic. And that also is preventing us from having very explicit constructions of these things, because like, how do you ever check that one of these local codes that you picked is actually robustly testable? That's quite difficult. All you're guaranteed is existence. So we don't actually know how large delta has to be, but a conservative estimate would be like at least in the hundreds or thousands, yeah.
All right, I don't see any more pressing questions, so maybe we can move on to the break. Continue with more correction later.